I should start by saying that it's close to midnight in the Netherlands, and the lights have been dimmed, so I'll try my best to stay coherent. So if anything is unclear, no, that's fine. I think the first problem is the worst one. Anyway, I'll continue on the topic of AGN feedback, and I will focus on a specific channel of AGN feedback. So far we've been talking about this in a somewhat general sense, but here I'll be really talking about this specific mechanism, which is radiation pressure on dust. Just a few words on how I've structured this talk. So I'll say just a few words, introductory remarks about where radiation pressure fits in among other AGN feedback mechanisms. And then I've split the main results into two sections. First, I'll show some very, very idealized simulations that were designed to compare against existing analytic models of radiation pressure. And then I'll show how the cosmological environment, in the second part of the talk, changes some of the behavior we see in these idealized simulations. But all these simulations are very idealized, so they were designed to tell us whether we should care about radiation pressure on dust as an AGN feedback mechanism. I've not aimed at reproducing observations or calibrating anything, and I'll just leave you with the conclusions at the end. So AGN feedback is something we should worry about, because when you look at the energy that's been emitted by the typical AGN over its lifetime, you find that this energy is on the order of 100 times higher than the binding energy of the host galaxy. So a different question is, what's the efficiency of AGN feedback? So by what extent does this 300 number go down? And the answer to that will depend on the AGN feedback mechanism. Okay, I'll try. There are various possible ways in which this energy is communicated to the ISM and the AGN. Here is just some of them. So there's jets, and I'll not be saying anything about jets. There's also nuclear winds. So when I came here 3 years ago, I gave a talk on this specific model. So this can be a very efficient feedback mechanism, but you probably need a very fast wind that generates an extremely hot bubble, and the observational evidence for this very hot bubble is not, well, non-existent almost. And then there's radiative feedback. There's various ways in which radiation can affect the environment of AGN. So there's photoionization, photoheating, X-ray heating, and all I'll be talking about is this specific model, as I've mentioned, radiation pressure on dust. This is perhaps also the most controversial of these, because in order to make this work, it's likely that you have to trap not only, well, you have to absorb UV photons, but you probably have to trap infrared photons as well, and I'll discuss that now. So how is this supposed to work? So suppose you have a massive starburst galaxy, a high redshift. It's very compact, and it's forming stars at a very high rate, so the dust mass is very high. The dust absorbs the photons emitted by the stars, but also by the AGN, in the optical and in the UV, and this gives you a force of L over C. So these models, by the way, here is the first assumption, assume that the dust and the gas is hydrodynamically coupled. I will stick to this assumption, not because I think it's always valid, but just for the sake of comparison with what has been done. But that gives you only a force of L over C. That is not perhaps strong enough. If you want more than L over C, you need the dust to be optically thick to its own infrared radiation. This has been investigated analytically in some very simplified numerical simulations. And just to sketch how this is supposed to happen, I've written a very simple Monte Carlo code that follows the transfer of infrared photons in optically thick regions. And this black line is the trajectory of one photon through a dense region. And you see that it undergoes a random walk until we can actually escape this region. And because of spherical symmetry, the azimuthal contributions to the momentum cancel out, but because you diffuse outwards, you pick up a positive radial component, and you build up radiation pressure as the photon scatters. So on the right-hand side, I show you again the photon, the momentum imparted by the photons as a function of the number of times it scatters. And the three colored lines give you three possible trajectories. So you see that it's very noisy. Sometimes it's even negative, but then it becomes positive. And the black line tells you what happens when you average that over 100,000 photons. So you see that it converges to exactly 5, which is, as you can see on the left-hand side, the optical depth. So the assumption that goes into these models is that when you have trapped infrared radiation, you get a force which is exactly tau L over C. That assumes spherical symmetry, that assumes a homogeneous field, that assumes the opacity is constant, and it also assumes this happens infinitely quickly. At some point, the radiation can be so efficiently trapped that the gas starts responding before you have time to build up enough radiation, and that will play a role in some of the results I'll show. So the aim of this work is to carry out numerical experiments, so I'm not even calling them simulations, and they aim at quantifying the importance of this mechanism as a feedback process. And I think there are two main ways of challenging this mechanism. There's the microphysics angle, so you can question the dust physics. Dust gets destroyed in the shocks, and if the gas is very hot. I will not be focusing on that, even though I think that's important. I'll be questioning it from an energetics point of view, whether this is something we should explore in the future. In order to do this, I've used a recent code called Ramses RT. So it's a combination of Ramses, which is an adaptive mesh refinement code, with radiative transfer, which happens with it's implemented with a moment method. So the radiation is modeled as a fluid. And in the first simulations I'll show, I'll start with a hydrostatic, a halo, an NFW halo with gas in hydrostatic equilibrium. The halo potential is static, but the gas can couple to the radiation. I include self-gravity, radiative cooling, and then radiation from a central AGN. In order to establish the link with analytic models and previous simulations, I assume that radiation comes only in two types. So there's UV or optical single scattering radiation. So this is the type of radiation that gives you L over C. And I also take one band that gives you a multi-scattering effect. So there's infrared trapped radiation. And instead of using black hole accretion, I run many different simulations in which I vary the AGN luminosity and also the light curve, and also other simulations in which I vary the optical depth. And you can see in the plot at the bottom, the typical optical depths we probe in these simulations as a function of time. So you can see it drops, of course, because as the shell expands, its column density goes down. And you see in some simulations we have optical depths of about 10, but we also were very brave and went up to optical depths of 1,000. Even though it sounds crazy, it's been probed in previous work, and it can show some of the interesting limitations this mechanism can have. So, as envisaged in the analytic models, the radiation pressure sweeps up gas into a shell and drives it outwards. So on the right-hand side, you can see a pretty image that shows the density of the shell and also the UV and the infrared flux. So the infrared is trapped within the shell and scatters inside it. And on the left-hand side, you can see various radial profiles. So you see the density, how the shell goes out, and you also see the radial velocity at the bottom. So this is just to give an idea of what the simulations look like. But the real goal is to compare them with analytic models, as I mentioned. And there are various groups that have studied this in quite a lot of detail. So there's a paper by Todd Thompson from 2015. This is also work that Wako Ishibashi and Andy Fabian have been looking at for a very long time. And they've written analytic models that give you precisely the equation of motion for a shell in an isolated halo that couples to radiation pressure in the UV and the infrared. So it's exactly what we need, and we can compare it with our simulations. So you see in both plots the radius of the shell as a function of time, and the simulations are shown, or the results for the simulations are shown with the colored bands, while the analytic models are shown with the dashed lines. And on the left-hand side, we have simulations that only include UV, so single scatter radiation. On the right-hand side, we include the multi-scattering infrared radiation. You can see that in both cases, the match with the analytic solutions is extremely close at high AGN luminosities. At low AGN luminosities, which is shown by the blue line, you have a discrepancy at late times, which is caused by the ambient medium pressure, which is usually ignored in the analytic models. This can confine the outflow and make it less efficient. But in terms of comparison, this is very encouraging. It also tells us that the code is well suited to do this in a more complicated setting. Now comes the interesting thing. This match goes away when you increase the optical depth to very high values. And this is what we're varying here. So this is again the radius of the shell as a function of time. And this is for a constant luminosity, but what I'm varying here is the optical depth. So the blue one is an optical depth of 10, and then we go up in factors of 10. So the red lines, so the red shade is optical depth of 100, and then the green one is an optical depth of 1,000. And you see that there's also a disagreement at early times. It seems that the analytic solution would progress faster than we get in the simulations. And the reason for that is because, for some reason, and I'll tell you in a second what I think this is, the shell in the highly optically thick regime is not absorbing as much momentum as we would predict. So you can see on the right-hand side, we compare the momentum input rate as a function of time. We show both the optical depth in the shade and the momentum in the simulations. And you see that this agrees well in the blue and the red cases. But in the green case, which is this 1,000 optical depth scenario, there's an initial discrepancy. And we thought about why this is the case. If you have extremely high optical depths, then the diffusion time of the photons is also very long. And what that means is that the gas configuration can start responding hydrodynamically before you have time to build enough radiation pressure. And there's a more precise way of quantifying this, which is to compare the timescales. So there's the trapping timescale, which is the characteristic time it takes for the photons to diffuse through the optically thick region, with the dynamical time or flow time. And I like to call it hydrodynamic response time. I think it's more accurate. And you see that in the cases in which we have moderate optical depths, the trapping times are always much shorter than the flow times. But in the green line, you see that there's an initial phase in which the trapping times are far too long. And what that means is that the radiation pressure cannot catch up. The shell just gets ejected, the column density drops before you have time to undergo enough collisions. And that can be, in this case, it's slightly academic, but it can be interesting once you include other feedback mechanisms. It could actually prevent this from becoming efficient if the flow times are already short. You can actually try to include this in the analytic models. So if you include a suppression that depends on the trapping time over the flow time, we now get the thick black line, which agrees much better with the green shade with the numerical solution. So the real thing is what happens in cosmological simulations. Again, these are very idealized. We deliberately kept the physics we've included to a minimum so that we can cleanly study how radiation pressure affects and drives outflows in these simulations. So I've taken a very massive halo at redshift 6, so it's 3 times 10 to the 12 solar masses. This is the kind of halo we expect a bright quasar to form. We include radiative cooling and star formation in a very primitive way. And we again include just these 2 radiation bins, again, UV, optical, and the infrared, so single scattered and multi-scattering radiation. We do not include supernova outflows. Again, that is important, but that will contaminate the outflows driven by the AGN radiation pressure, so we're doing that in the next simulations, but this is just to tell us whether we need to do this or not. Just to say, we turn on the AGN at redshift 6.5, and at that time, the galaxy looks as follows. So it's in the center of this complex network of filaments. It's extremely compact. We've seen this even in simulations with lots of feedback. It's very difficult to prevent these galaxies from becoming compact. And by compact, I mean the stellar component has a peak circular velocity of about 500 kilometers per second, in an effective radius of about 600 parsecs. So extremely compact, crazy object. Maybe you need that to grow the black holes to 10 to the 9 solar masses quickly anyway. And it's so compact that when you draw lines of sight from the center in all directions, we actually predict using opacities in the infrared that are typically adopted in the literature. We predict that to be optically thick in the infrared in all directions. This is, on the right-hand side, you see the optical depth distribution as a function of the polar angle. So you're looking at so pi over 2 is the disk plane, and you can see the poles, and you see that in all directions we get optical depths in the range of 20 to 40. We've tried adding supernova feedback. This does not go away. It's actually very difficult not to get this. And I should also say this converges very quickly with radius. It's really dominated by this central galaxy. I can say already that everything that we find that is related to radiation pressure is due to the main central galaxy. This is not affecting the halo. So, again, we do not include black hole accretion. We have various simulations with various AGN luminosities. And what I'm plotting here is the velocity of the outflow. You can look just at the one on the right-hand side. So that's roughly the maximum velocity of the outflow. as a function of the AGN bolometric luminosity. And the blue line shows what happens when you have single scattering only radiation. You do get an outflow eventually, but you need a luminosity of about 2 × 10 to the 48 lux per second, which corresponds to a black hole mass of more than 10 to the 10 solar masses. So it's very implausible. Too high. You need much more than L over C, you know, to produce an outflow in this kind of system. And quite remarkably, when you include the infrared, you get to the red line, which shows that you can now get outflows. A luminosity is a factor of 4 lower. So if you have an AGN with a luminosity of 2 or 3 × 10 to the 47, so a black hole of 2 to 3 × 10 to the 9 solar masses, a redshift 6, and that is more reasonable, we now start driving outflows. So what does this say? It says that when single scattering radiation is not strong enough to drive an outflow, the infrared multi-scattering radiation can launch it. The outflows are, even despite the optimistic assumptions we made about dust and the AGN being on all the time, the outflows are powerful, but only for a very short period of time. So you can see that from the mass outflow rate as a function of radius. So the different colors are different times, and you see that it reaches at most 10 to the 4 solar masses per year, but that only lasts less than 1 megayear, and it quickly drops with radius. That also tells you that most of the mass is not being launched out of the halo. It stays in the galaxy because the radiation just leaks out. And the shaded regions are the outflow rates for the gas which I call cool or cold. It's the coldest we have, so 10 to the 4 Kelvin. And that tells you that there is plenty of this cold gas moving in the simulations. I'll tell you in a second where that comes from. Most importantly, what does that do to the star formation history? So you can see with the dotted line when the radiation kicks in. The green line is this crazy luminosity UV-only simulation, and you see that it tracks the black line, which has no AGN very closely, whereas all the colored lines show what happens with infrared. So even a luminosity is 6 times lower than you need to regulate the galaxy in the UV. The infrared radiation pressure is already regulating star formation by factors of about 2 or 3. If you look at the innermost region of the halo, you can see that on the right-hand side, so the enclosed star formation rate as a function of radius, it actually completely kills the star formation rate. I'll skip that. Just I mentioned that there's a great amount of cool gas. I'm plotting here the PDF. So this is the mass as a function of the temperature in the outflow. And you see that there's a broad distribution of gas at different temperatures. But the dominant temperature is 10 to the 4 Kelvin. We've tried to work out why there's this cold gas, because people see a lot of cold gas and observe outflows, and there's typically 2 main ways of getting it out there. And it turns out that most of the outflow, you can see that on the right-hand side, has cooling times which are much shorter than the flow times. So the dominant mechanism for the formation of cool outflowing gas in these simulations is cooling of shocked ambient gas. And I'll just leave you now with the summary and the conclusions. Just to highlight the main ones, it seems that in very massive, compact galaxies that have redshift, from an energetics point of view, infrared radiation pressure is important. Even despite the optimistic assumptions we've made, it's only important in the central region, so it's not affecting the halo as a whole. The star formation is completely quenched in the innermost kiloparsec, but not much reduced elsewhere. And finally, we find that the outflows are naturally multi-phase, and that this cool phase forms within a few megayear through radiative cooling of the shocked outflowing medium. And I'll leave it at that. Thank you.
One quick comment, we can chat more later, but I've been talking with Eva Stryker and Jim Stone, and there's an issue that I don't know if you're aware of the standard implementation of M1 and all the moments space methods. If you don't resolve the UV-HiPACC, you can numerically fairly badly suppress the single scattering chart. And I think we've come up with a slightly pushy way to fix it.
Yes, so I think Yoki has looked at this before. So I think you can boost it in the central regions, basically, to account for this problem. And because we only have one source in these simulations, we do this without danger. But I think in the future, when we include more sources, it will be useful to know what you think about it. But that's true, yeah. And we're trying to account for that. Yeah. Yeah, so it's a good question. So we don't have a cold phase in the simulations, so the ISM will be naturally overpressurized. So there's two things we've done about this. One of them was to actually just remove the pressure floor and get some clumps, and we still found it to be quite efficient. But that still is at quite poor resolution. So the other thing we've done is using this Monte Carlo code I've shown, I've played with the distribution of the interstellar medium. And the answer really depends quite sensitively on the size of the clouds, mainly on the ratio of the size of the cloud to the mean free path of the infrared photon. So you can have anything from leakage, and I agree, I think that might be a major uncertainty in these simulations. But if you have very tiny clouds, and I'm thinking of this McCourt fog picture, it's possible you can actually trap it. Yeah. We should keep. Yeah, so we want to know that. We still haven't looked. So I think the best way will be to add some sort of passive scaling and trace it in time. I haven't looked at it. I think most of it just falls back. But what we know is it doesn't go much beyond half of the virial radius. But it either stays hovering in the halo, most of it just falls back.